This video lecture note is for Greenberg examples 15.5.1 and 15.5.3, which are computing the surface area of a sphere. 15.5.1 is using spherical polar coordinates, and 15.5.3 is using the naive parameterization of the surface in terms of writing the height as a function of x and y. So briefly, if we recall the polar description of the sphere, so this is 15.5.1. Using the polar representation, we can write x as a function of phi and theta. Again, remember, phi is the polar angle and theta is the azimuthal angle. Phi is like the latitude, theta is like the longitude. So x is equal to the sine of the latitude times the cosine of the longitude. Y is equal to the sine of the latitude times the sine of the longitude. And z, of course, better not depend on longitude. It's just the cosine of the latitude. So using that description, we can construct our unit vectors are phi, which we found, if you recall, to be cos phi cos theta in the I hat direction, cos phi sine theta in the y direction, and there's a negative sine phi in the k hat direction. So that means if we change the latitude when we're at the equator, we're moving straight down. That's this last term. And then finally, our theta equals negative sine phi sine theta I hat plus sine phi cos theta j hat. And there's no component in the k hat direction. That means when we change our longitude, we're not moving up or down. So the surface element, the cross product, we can work out. It turns out that r phi cross r theta, the magnitude of that, as we did in class, you can just take the cross product of those two things. You do some simplification after trigonometry, and it will tell you that is equal to sine squared phi square root. And so since phi only goes from 0 to pi, sine is always positive, so the square root of the square, that's always just going to be a, we can just write that as sine phi. Okay, so if we want to integrate, so for instance, example 1 and example 3 ask us to find the surface area just of the northern hemisphere in one of the 4 quadrants. So this should be 1/8 of the total surface area of the sphere. We know that the surface area of the unit sphere is 4 pi, so the answer better be pi over 2 if we know the total surface area of the sphere. But so let me just sketch. We're interested just in 1 quadrant of the northern, 1 quadrant of the northern hemisphere. So if we think about the limits of integration on phi and theta, our limits of integration on both of them should be going from 0 to pi over 2. Right? Phi goes from 0 to pi over 2 because we're just in the northern hemisphere, and theta goes from 0 to pi over 2 because we're just thinking about a single quadrant. So my integral, so if I want the area, I'm just integrating 1, and then my measure of integration is sine phi d theta. Theta is going from 0 to pi over 2. and phi is also going from 0 to pi over 2. So it turns out I can do the integral over phi immediately. That just gives me a factor of pi over 2 because the inner integral doesn't depend on phi. And then I'm still left with my integral over theta. I'm sorry, this should be a, I'm sorry, that is a sine. I'm sorry, I misspoke. It doesn't depend on theta, so I can do the theta integral immediately, and that gives me a pi over 2. And I still have to do the integral over phi, and my integral over phi, so I have a sine phi d phi, just going from 0 to pi over 2, gives me 1. So the final answer is that I have pi over 2 for that one quadrant of the northern hemisphere. Okay, so this would definitely be the preferred way of doing the problem on the sphere. But of course, we can also use the naive parameterization, which is in example 3. So example 3. So here I want to write the height, z, as a function of x and y. And again, I'm going to depart a little bit from the notation in the book. I'll say that x tilde is just x, the horizontal position. Sorry, x tilde of x is just x. Y tilde, actually I should technically write this as a function of x and y, is simply x. Y tilde as a function of x and y is simply y. But then z as a function of x and y, at least for a unit sphere, is 1 minus x squared plus y squared. So we did some of this in class, but let's continue and do this all the way. So now to construct our vectors, our x, which again is partial x tilde with respect to x in the I hat direction, plus partial of y tilde with respect to x in the j hat direction, plus partial of z tilde with respect to x in the k hat direction. Okay, and since this is a naive parameterization, that means that term immediately goes away, and this term goes to 1. And so the derivative of, as we did in class, the derivative of z hat with respect to x is just x over z. So this would be I hat plus x over z. Technically this is z tilde, which depends on x and y, k hat, and then r y. Similarly, there's going to be no I hat piece, so let me just write out the full expression. So this would be the derivative of the x coordinate with respect to the y parameter, or the y variable. Now we have the derivative of y, the y coordinate with respect to y. And then finally we have the derivative of the z coordinate with respect to the y parameter, k hat. Okay, and now the derivative of the x coordinate with respect to y is going to be 0. The derivative of the y coordinate with respect to y is just going to be 1. And so this is going to be equal to j hat plus y over z tilde, which depends on x and y in the k hat direction. Okay, so those are our two tangent vectors on the surface, and if we take the cross product, we can get the normal vector. And I won't go through the details of taking the cross product. Just believe me that when you take the cross product of our x with our y, and I take the magnitude, I presume everyone can take cross products and take magnitudes of vectors. The answer will be square root of 1 plus x squared plus y squared divided by 1 minus x squared plus y squared. Okay. Now notice when x equals 1 and y equals 0, that means if I'm at the equator, we could have an issue here, so we just should be aware of that. It turns out that when I write my integral, that won't be a major problem. So now I have to think about the limits of integration. Okay, so if this is x and this is y, so z is going to depend on x and y, but I need to do now an iterated integral. So let me write the area is going to be an integral so the thing I'm integrating is 1. My measure of integration, that's the thing that I need to multiply, dx times dy by, is going to be 1 minus x squared plus y squared to the negative 1/2. That's just simply this expression right there. I've multiplied the numerator and denominator inside the square root by 1 minus x squared plus y squared to simplify a little bit. And I need to integrate that with respect to x and y. But now I need to think really hard about my limits of integration. So the inner integral, I should be considering integrating over x at a given y. So this will be x min as a function of y, and this will be x max as a function of y. And here we'll have y min to y max. Okay, of course I could have also written the inner integral as an integral over y as a function of x. It doesn't really matter in this problem, it's symmetric, so I can go either way. But we're integrating now just over, switch colors. We're going to be integrating, so this is x equals 1, this is y equals 1, and we're integrating just over 1 quadrant of the disk. And so if I've written it like this, what I'm telling you is that I need to do an integral over x for every value of y. So I need to be thinking about the limits on x, which will depend on y, right? So this point over here is x min as a function of y. This point over there is x max as a function of y, okay? And so I know that I can write x. So this arc right here is a disk. So x max squared plus y squared has to add up to 1. So there I can write x max as a function of y. So x max is equal to the positive square root of 1 minus y squared. And that has to appear as my limit when I write my iterated integral. So the integral over x will run from x equals 0. So x min is always 0 regardless of y, but x max will depend on y. Okay. So I went into a little bit more detail than the authors of the book, but the answer is that when you do this, you should end up with a value of, when you do that correctly, you end up with pi over 2 as the answer. So you see the pi over 2 matches with the pi over 2. But I would argue that this procedure right here, where we didn't have to think so hard about the limits of integration on theta and phi, it's much more natural in a spherical description to think about theta and phi than it is to think about x and y, where the limits on y will depend on the value of x, whereas over here, the region that I'm integrating over, the limits on theta do not depend on phi, or vice versa. So it's very simple. So you look at these limits, they don't depend on each other. So the procedure is much simpler, but this procedure here is not the end of the world, and it does give you something consistent. So that is an example of how different parameterizations of surfaces when computing surface integrals will lead to different procedures for iterated integrals to solve the problem.